Joining me today is Dr. Dante Lauretta, principal investigator for NASA's OSIRIS-REx mission, which successfully retrieved geologic samples from the asteroid Bennu in 2023. He is Regents Professor of Planetary Science and Cosmochemistry at the University of Arizona's Lunar and Planetary at the University of Arizona's Lunar and Planetary Laboratory, and he's now director of the University of Arizona's Astrobiology Center. Basically, he's who you call when you want to know what rocks that aren't on Earth are made of. Dante, thank you so much for joining me today to talk space rocks. Can you start by telling me what led you to study the least accessible rocks in the solar system?
Yeah, thanks, Jess. It's really great to be here, and I'm excited to share this story. I was always an explorer. I grew up in the middle of the Arizona desert with no television and not even running water. We had to haul our own water from miles away, the big 500-gallon tank. And I just fell in love with the natural history, the geology, the unique flora and fauna that we have in the Sonoran Desert, and also the people who came before me. I would find Native American structures, petroglyph walls, old mining operations. And so I started to think about the past and who was here before me, and then who was here before them, and how far back can you take that question? At some point, there was nobody, nothing was alive on our planet. And I really became fascinated with that whole concept of the formation of the Earth, other planets in our solar system, and did they ever have life? And how does this phenomena, which we all kind of take for granted, it's all around us right now, but when you really think about it, it's amazing and it's a huge mystery. How did the origin of life occur on Earth? And especially when we know the early history of our planet was very violent. There was huge impacts. One was so large it spun off our moon. The planetary surface was a magma ocean. It was a very inhospitable world, yet somehow water became oceans, molecules became our atmosphere, and organics transitioned from something that was not alive to something that was alive. And as I dug into that question, it became obvious that some of the answers probably resided within asteroids.
Wow, and I actually really relate to a lot of that origin story. It's that insatiable need to know. Well, what about this? What about that? How did it happen? How did it form? How was it all created? And so I definitely get the impulse. And yours went back even further. Mine kind of stops with the primordial magma, and is fixated on Earth. Not to say I don't love a good space rock. So that's where our careers have really been different. So I know a lot about initiating research projects on Earth. How does one go about initiating a research project that requires space work? So if you could walk us along the multi-year path, that would be great.
I was really fortunate when I got to the University of Arizona in 2001 to have a very invested mentor, Dr. Michael Drake. He was the director of the Lunar and Planetary Laboratory and the individual who hired me. And we really clicked. He was about 25 years older than me. So we had this fantastic mentor mentee relationship. We were interested in similar problems. He was studying the early Earth and the formation of the core and looking at how metals partition from the mantle into the core of our planet. And I was interested in these more primitive meteorites, the things that accreted to produce the Earth, and then ultimately the ones that brought water and organics to our planet. And he was approached by Lockheed Martin, which is an aerospace company that has a line of business that builds spacecraft in support of NASA deep space exploration missions. And in 2004, the University of Arizona partnered with Lockheed Martin, had won a contract for a Phoenix Mars lander. And they were targeting the polar regions of Mars, and they were going to dig down and find the ice. And so Lockheed came back to Arizona and said, we want to partner with you on an asteroid sample return mission. And they approached Mike to be the principal investigator. And Mike immediately called me and he said, I want you to come in as my deputy. And that kicked off a 7-year odyssey to convince NASA to fly the mission. These missions are competitively selected. The first opportunity was 2004, and you have to write a proposal for a complete mission concept, from the rocket to the spacecraft to the science instruments to the operations to the sample curation facility and sample analysis, all the communication and public engagement, cost management, schedule management, technical management, scientific investigations. And Mike knew if we were going to be able to convince NASA to fly this mission, it had to target these carbon-rich objects, and it had to address these fundamental origins questions. And I was the individual that he brought in to lead that part of the science investigation. We spent 7 years writing and getting rejected and revising our proposal until the year 2011, when we finally won the contract to fly the spacecraft. That was in May. And unfortunately, Mike passed away in September of that year, creating a huge hole in my life because I love this man, and he really had brought me up into the professional ranks that I have achieved. And I took over as the principal investigator of OSIRIS-REx and have been leading it now for the past 13 years.
I was going to ask you about that, specifically about how working on a project with objectives so far in the future that people actually die over the course of the project. And then how does that change how you perceive the impact of your research? I mean, it can take literal lifetimes for these things to come to fruition.
Yeah, I celebrated my 20-year anniversary on OSIRIS-REx this February. And absolutely, part of it, you just don't think about how long of a timeline you've signed up for because there's a lot of immediate tasks in front of you and you've got to get them done. And the good news is the job has been very different from the proposal phase where you're like a startup company with a small team and you're scrappy and you're trying to sell this concept and convince yourselves as much as NASA and your other stakeholders that you can do it, to winning and then realizing we actually have to do this now. We promise. And it was kind of a theoretical exercise in the proposal phase. And then you're like, we have to build a robotic spacecraft to send it off into deep space. And you go through this rigorous design. There's tons of engineering meetings. You're looking at what has flown before that you can use, what is new that you have to develop. And then you get into building the thing. And I loved it. As a teenager, I was really into cars, and I didn't have a very good car, so I kind of had to learn how to fix it to keep it running. And it felt a lot like being in the garage with your buddies, except instead of a $400 1976 Plymouth Duster, I had a $400 million robotic asteroid explorer sitting next to me there. But I became really good friends with the engineering technicians that were assembling the spacecraft. I got to see OSIRIS-REx come into being. And it was just this phenomenal experience of seeing what seemed impossible take shape. And of course, you get it on that rocket, and there's nothing like launch day. I mean, your whole career is now invested in a giant pile of explosives that's sending your vehicle off into outer space for 7 years. And then you arrive at the asteroid, and you really are a team of adventurers, right? You did your best to plan the expedition. You brought all the tools you think you would need. The only thing you can fix or change is your software, which we had to do quite a lot of. But you're exploring this fantastic world that nobody's ever seen before. And it's just this, I was a big reader of fantasy and science fiction. And it just felt like that, like you just arrived at this other world that was fantastical and so alien and different than anything you'd ever experienced before, that it was phenomenal. And I love that part of the mission. I still think back on it with great fondness. And then, of course, the bringing the sample back down through the atmosphere, that was a nail-biting experience just last year. And now we're exploring that same world, but at a whole new scale with our electron microscopes, in some cases down to the atoms that make up the minerals of this asteroid. So it's been a phenomenal journey, one I document in my memoir, The Asteroid Hunter. I invite our listeners to join me on some of the details there.
Yes, I actually need to read it. So thank you for giving me something to read when I'm traveling in the next few weeks. So good recommendation. And so before I ask you to kind of lead us through some of the more exciting, dramatic parts of the mission, I'd love it if you could tell me what made the asteroid that was selected, Bennu. Why was this one so appealing?
Yeah, we chose Bennu as the target of the mission back in 2005. So now almost 20 years ago. It was discovered in 1999. And right away, it got scientists' interest because it's in a very Earth-like orbit and, in fact, has a substantial probability of impacting the Earth about 160 years in the future. So it shot up to the top of the planetary defense list. as a key object of interest. And that made it accessible. So it's kind of two sides of the same coin. We were looking for an asteroid in an Earth-like orbit because you need to launch off the planet, rendezvous, and spend a substantial amount of time, a couple of years. We were at Bennu, and then leave and come back to the Earth. And if you try to do that with an object in the main asteroid belt, which is in between Mars and Jupiter, it's much more expensive, both in time and in energy. It would take several decades to lead a sample return mission out to the asteroid belt. So the near Earth objects are kind of tumbling in. They're pieces of the asteroid belt that have migrated into the inner solar system, primarily through gravitational interactions with Jupiter and Saturn, as well as this phenomena called the Yarkovsky effect, where sunlight can slow down the orbital velocity of an object, moving it into the inner solar system. So the orbit was a big part of our selection criteria. And then we got to think about how big of an object do we want to go to? Because there were several hundred asteroids that fit the orbital criteria. Many of them are really small, like 10 meters. And we thought that would just be really hard to operate around and try to get a sample. It's probably just a solid boulder. So you'd have to break it or shatter it or some kind of chip it away. So we said, let's go to something reasonably large. And we chose the value of 200 meters or bigger, because when we look at the asteroid population, objects that are smaller than that tend to rotate really rapidly, like sometimes more than once per minute. And that also would imply they're a coherent object. And then when you get to bigger and bigger objects, Bennu's about 500 meters across. They're rotating relatively slowly. Bennu's rotational period is 4.3 hours. So there was a few dozen asteroids that kind of fit all of those constraints, the orbital constraints, the size constraints, and the rotation constraints. And it finally, science got to come in and say, hey, we're interested in the origin of life, the origin of habitability, oceans, atmospheres. We need to go to a carbon-rich, water-rich asteroid. And there was only 5 that we thought had high confidence of meeting that criterion. And Bennu was very well characterized, especially in 2005. We had a custom astronomical campaign using every major telescope you can imagine: Hubble, Spitzer, Arecibo, Goldstone, tons of glass all over the world was on this thing. So we had a really great knowledge base, and we were able to use that for our operational planning. And so it kind of reduced risk in that manner. So carbon rich, relatively large, slow rotator, Earth-like orbit, all led to Bennu as the prime target for the mission.
That makes a lot of sense. And actually, when you were describing what the selection process was like, it almost made me think about like when you date someone. They have to, if you want to pursue a relationship, you got to make sure they check all the boxes. And it sounds like that's you guys basically set it up so you were dating an asteroid. um,
Indeed, and it felt a lot like that. It was at times a love-hate relationship, I guarantee you.
I think a lot of us have been there, but in a little bit closer to home
Right,
situations.
right.
So I want to talk about actually kind of the implications of what you're studying. But first, I was hoping you could take us to the day that you were physically there when OSIRIS-REx touched back down on Earth after all of these decades of planning and execution. Could you describe the scene for me? Because I was watching live, the world was watching, and you and a select group of other people really knew how much was at stake. I mean, the decades that went into it, the millions of dollars, people's lives, and all the knowledge you hope to get. So just give us that experience. Kind of let us ride on your coattails through it.
Yeah, that was September 24th of 2023. And I woke up in a Holiday Inn at the Dugway Proving Ground, which is part of the U.S. Department of Defense's Utah Test and Training Range, which is just southwest of Salt Lake City. And this is the largest continuously controlled airspace in the continental United States. The military uses it for all kinds of testing and training scenarios. And that's why we chose it, because we had the flight path that was coming in over California, across Nevada, and then into Utah for touchdown in the Utah desert. I woke up really early in the morning, like 1:30 a.m., because we had spacecraft operational activities, particularly to command the release of the capsule targeting the Earth. We were about a quarter of the distance between the Earth and the Moon when that capsule was released. And this is a dumb capsule. It has no guidance capability whatsoever. You use the spacecraft to line it up, targeting Utah from tens of thousands of kilometers away from the Earth. And then you give it a little bit of a spin to spin stabilize it through the atmosphere. And that was a little bit of a nail biting moment, because it wasn't guaranteed we would release the capsule, because we had to guarantee safety of the people in Utah, safety of the military assets. If we were off track at all, we would have had to have waved off, and it would have been 2 years to loop around the sun and come back to the Earth to try again. So it was an anxious moment. After almost 20 years of my life, we had to get that capsule released. I wear a fitness tracker, and my heart rate was 120 BPM when I woke up, which is like over twice my normal baseline. That's like when I'm really running or on my bike or moving fast. So I knew that I could just feel the anxiety of the day and just this career's worth of effort that was at stake here. So the spacecraft commanding went according to plan. We got the batteries powered up. These batteries are responsible for releasing the parachute system. And we hadn't talked to them for 7 years because they were passivated. They had this layer to prevent any voltage or current from flowing. So it was like, okay, are the batteries still there? They've been sitting in space for 7 years. Who knows what's happened? But they came online. And then we saw a successful release of the capsule. And I had a few hours. I could have, gotten back to sleep, but I was so amped up. There was no way I was getting any shut eye. I took a little bit of solace. I was teaching at the university during that time period, and I had a bunch of student essays in astrobiology to grade. And that kind of helped me out. I spent a few hours reading students' essays and giving them their grades. It was kind of a nice distraction. And it was a special OSIRIS-REx edition of the class. So they were getting remote lectures from Johnson Space Center and all these cool locations throughout the whole semester. And then I went down to the lobby. Some other team members, everybody was in pretty good mood. The operations had gone according to plan that day. And we drove out to the Michael Army Airfield, where there was a huge crowd that had gathered. There was all these high-level officials from NASA, from the military, from government, university, Lockheed Martin, lots of international partners from Japan, from Canada, from Europe were all there. So this big crowd of VIPs, my family, my wife, and my 2 sons were there to celebrate with me. And I get into a helicopter and we fly out to a staging area, and we're waiting to hear the call outs. There's a range control officer that's giving us the information. Capsule spotted over California, coming in at 27,500 miles per hour. We crossed the entire state of California in 2 seconds, right? And then over Nevada and then into Utah. And as soon as we got into Utah airspace, the helicopters take off. There was 4 choppers. The first one were the safety technicians, because we are in an active military test range and there could be things you don't want to mess with that are out there. And their job is to make sure the area is safe for our operations. Helicopter 2 was the camera team. You said you watched the live TV show, so you had NASA camera footage from the helicopter. Number 3 were the Lockheed Martin technicians that were going to secure the capsule and get it ready for transport back to a clean room. And helicopter 4, where I was the environmental sampling team, because we're going after origin of life questions. The last thing we want is to pick up contamination in the Utah desert that spoofs us and says, oh, look, there's all this interesting chemistry and going on. And you're like, actually, that's mud from Utah. So we were going to sample all of those different components. I'm in the helicopter, and there's a critical altitude crossing of 100,000 feet where a small parachute called a drogue chute is supposed to deploy, because you're transitioning from supersonic flight to subsonic, dropping below the speed of sound, and the capsule's not stable in that low velocity. So the drogue comes out to kind of stabilize it. And I'm hearing 100,000 foot altitude crossing, and I tapped the officer in the front seat, and I was like, drogue? And she said, they're not calling drogue. And I'm like, oh man, my memory goes back to a disaster in 2004, a NASA mission called Genesis, which was collecting particles of solar wind, whose parachute failed to deploy and it cratered into the Utah desert. And there's a little memorial there that we visited at UTTR to that capsule. So I was thinking, okay, this is a disaster. All of this work is going to come down into a shattered remnant of our beautiful spacecraft. And I'm going to have to deal with it on live TV. I'm going to have to keep my cool when all I'm going to want to do is cry. And we go through 60,000 feet. and there's no drogue. And I'm like, okay, this is it. And then all of a sudden they say main chute spotted. And I was like, well, that's not according to plan. I said, but thank goodness, right, that this thing finally opened up. It came in really low in altitude, but it was enough to slow it down and land this capsule. So I just broke into tears in the helicopter. All this stress that I didn't even know I was carrying for the past 20 years just released. And I was like, we did it. I mean, when we first talked about this in 2004, it seemed like magic. Like, really, I can pick an asteroid, any asteroid in the solar system, and I'll get samples back in my laboratory? No way. There's no way that's feasible. Sure enough, on that day, the dream came true.
That is absolutely wild, and what a catharsis. Because I do remember one of the most striking images that I took from watching you all do that was you were running to it, with your arms in the air, like, you just won the Super Bowl. And that was really cool because I think for so many years, people have thought that scientists are boring usually old guys in lab coats that never leave the lab, and they're very dry and don't get emotional. But you and your team really helped show the world like the all of the essence of yourself that you put into this work. And so I wanted to thank you for being so expressive, because that really helps the world understand what we as scientists go through. I mean, these are like our babies. They're just our career babies.
Oh yeah, and we're very passionate. We're artists, right? And our art is expressed in a different way because we are expressing the human condition, our curiosity, our wonder at the universe, the amazement that we all feel when we truly appreciate natural systems and what they represent, how old they are and how complex they are, and how fortunate we are to be here, to be able to appreciate, to learn, and to share that knowledge. So, and I thank you because I mentioned it before, but you were one of my inspirations when I got to writing my book. Yours was one of the ones I pulled off the shelf to say, okay, how do people tell these stories? And yours was one of my favorite. So,
oh, well, thank you so
Misadventure,
much.
if you guys haven't read it, I would highly recommend it. Jess has done some crazy stuff, and she tells the stories really well. I was with you there through many of those wild rides that you took us on in that book.
Well, I mean, that's kind of why we do this whole show, right? I mean, it doesn't matter all the amazing research we do, and all the cool discoveries and the failures that we learn from. None of it matters if we can't tell the stories. So that's why I really appreciate you coming on my show here and telling the folks who support us at the Union of Concerned Scientists that, like, yeah, we have optimistic things to talk about, and successes. And we learn from the failures, but the successes are pretty great to celebrate. So I do want to go a little ultra nerdy here. And you mentioned it, you kind of teased it before about what the samples from a carbonaceous asteroid can tell us about the origins of our universe. And so geek out. Tell me about the mineralogy, the geology, anything that you've learned so far, like lay it on us.
The sample is awesome. I mean, we are having so much fun analyzing this material. It's exactly what we hoped for, and it's full of surprises. So it's dominated by a class of minerals called phyllosilicates, more commonly known as clay minerals. We're seeing lots of a material called serpentine, and also another clay called saponite. That makes up about 70 to 80% of the volume of the samples. And these are really interesting structures. The serpentine, as the name implies, kind of has this fibrous morphology like a snake. And asbestos is an example of a serpentine kind of mineral. This isn't asbestos that we have in the samples, but it's related, and it looks fibrous like that. We have lots of carbonates. This is carbon in mineral form. A lot of people are familiar with it. If you live in an area with hard water and you get those white crusts that clog up your shower heads and your faucets, those are carbonates. You have carbonated water or soda water, right? Carbon dioxide in the water. And you have typically calcium, which makes it hard. And then calcium and the carbonate bond, and that forms a mineral called calcite. We're seeing a lot of calcite, but we're seeing a lot of other carbonates as well. Magnesium-rich carbonates, iron-rich, manganese-rich. They look like evaporite minerals. And we kind of intuited that they would be there from our exploration of Bennu, because even though it's generally really dark, which is what led us to assume it might be rich in carbon, some of the boulders had these big, like meter long veins of highly reflective, bright white material. And our spectrometers indicated they were probably carbonates. So this is showing you had extensive kind of hydrothermal alteration a long, long time ago, not on Bennu, because Bennu is too small to support something like this, but a larger asteroid that we've realized Bennu is just a small fragment of, something that was blasted off in a giant impact probably 1 billion years ago in the main asteroid belt. We're seeing these beautiful crystalline iron oxides called magnetite, also known as a lodestone, and also crystalline iron sulfides called pyritites, which are related to a more common mineral on Earth called pyrite or fool's gold. And they look a lot like that kind of brassy, these are hexagons as opposed to pyrite, which generally makes cubes, but a very similar kind of chemistry and a similar kind of formation. Again, hydrothermal deposition. It turns out it's very rich in carbon. About 4.7% by weight of the sample is carbon. Only 10% is in those carbonate minerals. The other 90% are in organic molecules. We're seeing all the nucleobases that are used in DNA and in RNA. So the letters of the genetic code are in this asteroid. The other major biomolecule are proteins, and we use 20 amino acids commonly in biology on Earth. If you take protein supplements, you can usually see which amino acids are in there. We have 13 of the 20 amino acids so far have been detected in the Bennu samples. We're seeing these really intriguing structures we call nanoglobules. They're little spheres. They're fluorescent. So if you put it under UV light and you have a fluorescence microscope, they light up and they look like little bright specks throughout this dark matrix. And then we zoom in. They're sometimes hollow. Sometimes they have minerals inside of them. Maybe even fluid is trapped inside of them. So they probably were like oil droplets in this hydrothermal system on this ancient asteroid. And then the big surprise so far has been we did find white encrusted stones that I thought was going to be those carbonates, but they turned out to be magnesium and sodium rich phosphates. And phosphorus, which makes up the phosphate mineral, is also a key element in biology. It makes up the backbone of DNA and RNA. It makes up a key component of cell membranes. And when you get to animals, it makes bones and teeth. So that's also really interesting for early life studies. When we put all of that together and we think about environments on Earth or elsewhere in the solar system where you get the same kind of minerals, it looks a lot like what's forming at the alkaline hydrothermal vents at the mid-ocean ridge on Earth. And we're seeing very similar mineralogy coming out of the plumes of an icy satellite called Enceladus around Saturn. So I think we have an ancient hydrothermal system from an icy ocean world, probably formed in the outer solar system because you needed to get the carbon dioxide ice. And we're seeing a lot of ammonia, which is a very volatile element. So you had to form this thing probably around Saturn. And then it had to migrate into the main asteroid belt, get shattered. Bennu is just a scoop of all of the fragments that broke off in that catastrophic disruption, and then has migrated into the inner solar system where we were able to retrieve it and start to piece this very complex history together.
Okay, so I have to say that is one of the most mind-blowingly cool things that I've ever heard, like without a doubt. And I've heard some cool stuff over the years, but that is so exciting. I was actually having to tell myself, "You're on camera, sit still, don't jump up and down and be like, oh my God, I'm driving to Tucson right now because I want to see this."
Right.
So, the fact that, I mean, obviously I have a professional interest in this, but the way you describe it really touches on what makes studying things like Bennu so important for our understanding of the origins of life on Earth, what the solar system was like when these things formed. So if you can get a little bit specific, even more than you already have, about what this understanding of conditions were like on Bennu when it was formed, how does that help us with our efforts to piece together our understanding of Earth itself?
Well, it's clear that water and key organics and nitrogen were delivered to the Earth by these kinds of objects. So they are responsible for our planet being a habitable world, as opposed to just, no offense, a volcanic encrusted object, right? So
None taken, none taken.
these kind of transitioned us over from being a dry, pretty inhospitable place to this beautiful paradise that we enjoy and live in and thrive in, and hopefully will take care of, so future generations can do the same thing. And the other thing it implies is that these components of habitability and prebiotic chemistry were ubiquitous across the solar system. The Earth wasn't the only place that they were delivered to. Venus would have had a substantial inventory, and there's strong evidence that Venus had oceans early in its history. Mars would have had the same kind of inventory. Definitely icy satellites, dwarf planets, things like Ceres, Europa, Enceladus, Titan, all of them would have had the chance for the origin of life to occur. So you start to ask the question, did it? Is there life today on Mars? We know Mars went through massive climate change, but life could have migrated to the subsurface where we find organisms on Earth today. What about Venus? Venus is now a hot, hellish pizza oven kind of surface temperature. But if you get in the upper atmosphere, it's similar to the conditions at the surface of the Earth. So maybe life migrated up. What about Ceres? What about Europa, Enceladus, where we know we have oceans under those ice caps? There's hydrothermal vents. Let's try that again. There's hydrothermal vents and plumes erupting into space. One of them makes the E-ring of Saturn. So the hydrothermal chemistry we're seeing on the mid-ocean ridge on Earth, and we saw occurring in Bennu's ancient history, is happening today in the outer solar system. I'm optimistic that there's some form of life out there because every one of those objects had the chance. And the question is, what are the odds? What does it take to go from this clay-rich, organic object into something that's alive? And to me, that is the most profound scientific mystery we're facing because we have no idea. We can't make that happen in the laboratory. And that's why we're driving into the astrobiology investigations that we are.
It is so exciting for the future, especially when we have so much doom and gloom news that keeps coming out. And I just love science and scientists as messengers of joy and enthusiasm and curiosity. So this is super exciting. I'm going to be jazzed like the rest of the day for sure, just from talking to you about it. So just to give us a sense of what all of this effort produced in terms of like quantity of material, how much total sample did you get? And then what are the technical analyses that you are running on the sample?
The mission requirement was 60 grams, which is about 2 ounces. And we brought back now 121.6 grams, so more than twice the mission requirement. And that is an enormous amount of material because of the kinds of analytical techniques that we have available to us. So far, we've requested a little over 8.5 grams and have only analyzed about 2 grams of sample. So we can do a lot with a small amount of material. And most of the analytical techniques are generally non-destructive. So the sample is still available for follow-on work. We do a lot of electron microscopy, scanning electron microscopy, backscattered electron microscopy, and transmission electron microscopy. And each one of those gets you different kinds of information and different scales. We look at it spectroscopically because that's the kind of data we collected using spacecraft instrumentation. Spectroscopy is, basically breaking light up into its constituent wavelengths, and different molecules and different minerals have different patterns, and you can match them to what you have in your library. And now we have the actual sample, so we're learning things like that phosphate was not detected at the asteroid, but we also weren't expecting it, and it probably wasn't in our library. So we're going back to the spacecraft data and saying, was it there and did we miss it? And now that we're smarter, can we find it on the surface of the asteroid? We do a lot of chemistry, bulk elemental abundances using a technique called ICP-MS, which is inductively coupled plasma. So you use a plasma to ionize the sample, and then the mass spectrometer sorts atoms by their charge to mass ratio, and you can measure the different isotopes of pretty much any element that you're interested in and there's different mass spectrometers for different mass ranges. We use ion microprobes, which allow you to go in and sputter little regions and create secondary ions at nanometer scales and learn about carbon isotopes, oxygen isotopes, nitrogen isotopes, hydrogen isotopes. And that's where we start to see that not only does Bennu have all of this interesting chemistry that was generated in these hydrothermal vents, but there's these very hardy grains of silicon carbides and graphites, which are pretty much immune to alteration under those conditions. And they formed around stars that existed before our solar system. We call these pre-solar grains, and they condensed in the outflows of supernova and giant stars that were shedding their outer envelopes. So we're getting firsthand information about nucleosynthesis and the death of large stars. And those grains migrated through the interstellar medium for millions of years before getting swept up into our protoplanetary disk, and then survived this very turbulent history, including scalding hot water circulating around. They're all resistant to that, to tell their story to us today on Earth. So those are just some of the techniques that we're using. The organic chemistry is largely done through gas chromatography, mass spectroscopy, liquid chromatography, mass spectroscopy, UV fluorescence, and some other specialized techniques that we've developed just for this sample, especially in extraction and amino acid identification.
Okay, so it sounds like you all have plenty of work to go too, because you've only looked at such a small portion of what you actually were able to retrieve. So this is going to keep some people, grad students, occupied for quite a while. It sounds like. So this is. It makes me want to know: would you yourself go to space if the opportunity presents itself?
Absolutely, yeah. Sign me up.
All right, so
So
you and I should go to Venus, because Venus is my favorite off of Earth place because of the volcanic activity. So you want to go to Venus?
yeah, you bet. Yeah, if you got a ride, let me know. I'm in.
All
I'm
right,
not sure
well,
my family will be on board with that, but we'll have some work to do to
I
convince them
mean,
of that.
just tell them you're going to another asteroid, and then oops, we decided to go to Venus instead because it presented itself.
Right,
But
right.
oh man, okay, so we're wrapping up here, and one of the things I really like to ask all of my guests, it's actually a two-part question, and it's because we are the Union of Concerned Scientists. So Dante, why are you concerned?
Well, I'm concerned because I don't think we really take the time to appreciate how lucky we are to be alive, to be aware, and to exist on this beautiful planet. I mean, we really have this gem that is, led through a very complex and turbulent history so that we could be here today. And I don't think people take the time to step back from the hecticness of their everyday lives. And I know people are facing all kinds of hardships and challenges out there, but it just changes your perspective when you realize space is a really big place. It's a really harsh environment. We haven't seen anything like the Earth in our exoplanets yet, and we're looking for them, and we'll probably find something like it. But we need to take care of this place. We need to take care of each other, right? Human beings are very special in our ability to communicate, our ability to remember the past, to predict the future, to develop these amazing technologies. But they come at a price, and we need to understand that. We're smart. We can solve any challenge if we just join together with a common vision, respect each other, respect our home world. And I'm concerned that is just not sunk in to most people on this planet. And we need to work hard to communicate those messages.
That is profound, and I completely agree. And so we don't end on kind of a downer because what you've done is so uplifting. What are you doing about that concern?
Well, I'm getting out there and I'm communicating. First of all, just the sense of adventure and what we are capable of. As I said, OSIRIS-REx seemed impossible when we first started talking about it 20 years ago. But we had to bring together a very diverse team, not just, diverse in profession, right? Because you needed scientists, you needed engineers, you needed managers, you needed business people, but ages, backgrounds, because you're solving really complex problems. And there's strength in that diversity. So you really come to appreciate people think differently than you do. People look differently than you do. They have different backgrounds. But when you unite on this common vision, there is nothing that is impossible. We can do amazing things when we join together, when we unify, and when we work towards a common goal. And that lesson translates across all aspects of our lives, right? It's not just space exploration, it's all these grand challenges that we're facing in healthcare, in immigration, environmental concerns. All of those can be solved when we unify, agree, and move forward together.
Hear, hear. So thank you so much for taking the time to talk to me, Dante. I know our listeners will absolutely love this conversation. And for anybody who's just hearing the audio, it's going to be edited down from the full version. So you want to go check this video out on our YouTube, because this is a fantastic talk. Thank you, Dante, and keep up the amazing, groundbreaking, trailblazing work.
Thank you, Jess. I will do my best.